Now let's move on to voltaic cells, which are also called galvanic cells. Remember that in a voltaic cell, unlike the electrolytic ones we've just been looking at, there is a spontaneous reaction. You don't need a battery to force the reaction to happen. It happens by itself and is itself actually the battery. Now here we have an example of a spontaneous redox reaction. Iron, like in a nail, reacts with copper ions. Copper ions are blue and they can dissolve, and here they are dissolved, they're in the aqueous form. And when these react, like when you put a nail into some copper sulfate solution, then the iron gets corroded away as the iron changes into iron ions. Ions of iron are soluble and they just can dissolve into the solution. They're not hard metals like iron atoms are. Very big difference between Fe and Fe2+. Meanwhile, the copper ions, which were blue and soluble, get changed into copper atoms, which are reddish brown, and that's what coats the nail. This is the situation after the reaction. We can see there are lots of iron ions now in the solution, and there's lots of copper metal coating the nail. You can try this yourself. It happens quite rapidly. If you take an iron nail or anything made of iron and put it into some copper iron solution like a copper sulfate solution, then you will see that after a short while there'll be a coating of reddish brown copper. Now for this, give the oxidation half reaction, the reduction half reaction, show the electron flow. Are the electrons going to the iron, away from the iron, to the copper ions? What's happening there? And why is this reaction spontaneous, whereas the one with copper chloride changing into copper atoms and chlorine molecules was not spontaneous? What makes this one spontaneous? Here we have the oxidation half reaction. Iron's oxidation number is 0. Iron's oxidation number +2. Oxidation number has risen. That means that this was an oxidation half reaction. Another way to see this is an oxidation half reaction is that electrons are lost in the process. The neutral ion must have electrons taken away from it to change it into the positively charged ion. And those electrons are then given to the copper ions, and that is the reduction half reaction. The copper 2+ ions, they have an oxidation number of +2. By being forced to take electrons, then that changes the copper 2+ ions into copper atoms with an oxidation number of 0. So we can see the oxidation number has dropped. It's been reduced. Or another way we can see this, electrons have been gained. That's another definition of reduction. So we can see that the electrons are flowing from the iron to the copper ions. Why is this reaction spontaneous? It's because iron is a stronger reducing agent than copper is, and so it's able to force the copper ions to take those 2 electrons from it, and in that way actually it makes the copper ions to become less stable. The copper ion form is more stable than the copper atom form. Always an ion form is more stable. It's not neutral, but it's stable because it's got an electron configuration like a noble gas an ion has, whereas an atom, except if it's a noble gas, doesn't have an electron configuration of a noble gas, so it's less stable even though it is neutral. So here the iron is actually becoming more stable because it's becoming an iron ion, and it's able to do so because it can give electrons, it can force electrons to go to an acceptor, even though the acceptor sort of accepts it against its real will, if we could say it like that. And the reason why it can force those copper ions to take those electrons is because iron is a stronger reducing agent than copper is. These 2 half reactions don't have to happen in the same container. One can happen in one beaker and the other in another one, as long as there is some kind of path along which the electrons can flow between them so that reduction and oxidation can still happen. And so all we need to do is provide an external circuit, a wire, joining the 2 electrodes where this can happen. Here we have an inert electrode which doesn't actually participate, but it just transfers electrons as needed. And here we have an electrode which actually does participate because the ion of the electrode changes into iron ions. And now this is actually really nice because by putting the external circuit there, a pathway along which electrons can flow, and by having these two half reactions separated like this so that the only way they can each happen is by electrons flowing along the external circuit, we have now created ourselves a situation where electricity flows. And so we could put some device in over here, maybe a bulb or something, and then we could, if the flow is great enough, cause it to shine. So in other words, this is a little battery that we've created over here. Now we just have a problem with it, and that problem is that as it stands now, we're going to have a build-up of charge. It's going to be a positive build-up around the iron electrode and a negative build-up around the copper electrode. And so that's going to cause the reaction to stop after a while. So how do we solve this problem? We solve this problem with a salt bridge. A salt bridge is an ionic bridge which connects the two half cells of a redox reaction in a voltaic cell. It's made up of some ionic substance. It must be an ionic substance in solution. So using something like sugar, which is a covalent substance, would not help, because when you dissolve sugar, it does not release ions. Each sugar molecule is just surrounded by water, but there's no charge there, and so therefore it cannot conduct electricity. But if we were to take something like sodium nitrate, as in this example, and we dissolve the sodium nitrate, we'd have sodium ions, nitrate ions, and these ions, being free to move because they dissolve, can conduct electricity. And in that way we have a complete circuit, and also we can see that the problem that I raised just now of the iron part of the half reaction becoming too positive because of the buildup of iron ions as the oxidation reaction happens, that problem will not be so great, because it will cause negative ions to flow in from the salt bridge, neutralizing the solution over there. And the same point, the problem that I raised about having a buildup of negative ions because the copper ions are being changed into copper atoms, therefore being removed from solution, leaving whatever negative ion was there in greater relative abundance because the copper ions which were neutralizing it have been taken away and changed into copper atoms. That problem of a buildup of negative ions will be removed by the flow of positive ions from the salt bridge in a way such as to neutralize that solution on that side as well. And so then the whole reaction would be sustainable.